Hi all, today we are going to discuss about transformer with magnetic leakage flux. Here I am taking the assumption that because in the previous class we have removed some of the assumptions. So last class we have considered the iron losses we have considered, and we have assumed that a finite permeability core or the permeability is finite. So these things we have considered in the last class. Here I am writing on a glass screen, so the handwriting doesn't come properly. So I am providing the complete handwritten material in the description of this video, so you can please download the material from there. Here you try to understand the concepts. So today's class we are removing one more assumption that we have taken, that there is no leakage flux, but practically some leakage flux will be there. Let us see what does this mean. So if I am taking a transformer, I have taken a transformer. So the transformer will have two windings. One is the primary winding and there will be one more secondary winding. So let us assume the primary winding is wound like this. This is my primary winding. So this primary winding is connected to some supply V1. Getting it? So now the secondary winding, let us assume this is my secondary winding. So this secondary winding is connected to some load. So now whenever the secondary winding is connected to load and primary winding is connected to some supply, under no load condition we have seen in last class that it will produce some flux phi, and this flux remains constant irrespective of the load. So let us assume that flux that is passing through the core I am representing by the term called as phi. So because of this flux, so EMF is induced in the primary as well as EMF is induced in the secondary. Because of this EMF induced when the load is connected, the secondary current passes in the load. So due to this current there will be load voltage or V2. This is because of the load impedance. So now in order to compensate for this current, we have seen in the last class the primary will carry a current that we have represented by I1 dash. That is represented by I1 dash. So this will be in addition to magnetizing component of current. Now because of this load current, what happens, because this current is passing through the entire winding, because of this the MMF is produced. Because of this, out of the MMF that is produced by this, because secondary current will produce one MMF, we have already seen that MMF if you represent by phi 2, primary will produce an MMF or the flux to compensate for this one. So that we have represented by phi 1 dash. So phi 1 dash is equal to phi 2 and always flux is maintained. But in practice, because of this current, whatever the flux is produced, all the flux will not pass through the core. Some flux will close here itself. That means some flux will leak like this, because the flux here, because through the air the reluctance is more, that's why less flux only passes or leaks like this. Most of the flux will pass through the core only. Similarly, in the secondary side also some flux will close here itself. It will not pass through the core, it will only link with the secondary coil. I am repeating again, because of the primary current, the flux that is produced, the entire flux is not passing through the core. Some flux will close or pass through the air itself, or we can tell it is only linking with the primary winding and it doesn't link the secondary winding. So this flux which is not linking with the secondary winding, that flux I am representing by the leakage flux, that is phi. L stands for leakage flux due to current I1, that is phi L1. Similarly, the leakage flux produced by the secondary winding which is not linking with the primary winding, that I am representing with phi L2. So now total fluxes if you are calculating in your core, so there is a flux phi 1. Because of this phi 1 only E1 is induced as well as E2 is induced in your core. Now coming to this leakage flux phi L1, this leakage flux phi L1 will link only with one winding only. It is not linking with the second winding. That means because of this leakage flux some EMF, extra EMF is induced. That extra EMF I am representing by EX1. That means total flux linking the primary winding will be the flux phi plus phi L1. That means it will be E2 will be induced, E1 will be induced as well as EX1 also will be induced. Similarly, in the secondary side there is a leakage flux phi L2. Due to this leakage flux, one more extra voltage will be induced along with E2, that is EX2. This X stands because it can be represented in the form of a reactance, because it doesn't produce any value of the power, it doesn't consume the power, actually it is inducing the voltage. So that I can represent with, it is due to the leakage flux or it is related to the flux, that's why I am representing in the form of a reactance. I hope you understand this one. So now what is happening, because of this leakage flux some additional voltage is induced in the respective windings, and this flux is not useful in transferring the power from one circuit to another circuit, because the major purpose of the transformer is whatever the voltage and current this current is passing, V1 multiplied by I1 dash, that should be transferred to the secondary, V2 multiplied by I2, but all the flux that is produced is not linking with the second winding, some flux is linking with the first winding only. So that is not responsible for the transfer of power from primary to secondary winding. Similar is the case, the flux that is linking in the secondary, that is not linking with the primary, or it is not responsible for any transfer of the energy. That's why these are called as leakage fluxes, and the EMF induced because of them is called as the leakage EMF, or the corresponding reactance, because it can be represented by a reactance, that is called as leakage reactance. So let us go back to what we have studied in the AC circuits. So in the AC circuits we have seen, let us take for example, one reactor is there or one inductor is there. I have given a supply V. So let us assume this inductor is having the inductive reactance of XL. This XL will be equal to 2 pi FL. It depends on the frequency of your supply. So let us assume the current I is passing. So I is passing like this. When the I is passing, the EMF will be induced in this. That let us assume the EMF induced in this is given by E. So this can be represented like this. If this is the current that is passing, we know the current will be lagging behind your applied voltage by 90 degrees in an inductor. Now because of this current is linking with this, because of the current, the time varying flux is produced. That flux links with its own coil and produces an EMF. So we have seen in the last class that EMF will be lagging behind this current or the flux, because flux will be in phase with the current by 90 degrees. So we can tell this is my value of E. Or we can tell the EMF induced is 180 degrees opposite to your applied voltage, or if you are taking the vector sum of V plus E will be equal to 0, or V will be equal to minus E, or this will be equal to j omega L into I, or this is nothing but XL is equal to omega L, j times of I into XL. So this is the value which is equal to the supply voltage. Actually the EMF induced will be equal to minus j into I times of XL. That means that j is indicating that it is leading the respective value. It is leading the respective value of the current plus j. So minus j means it is lagging the respective value of current. Or we can tell that E is equal to minus j omega L into, this is XL multiplied by the current. This negative sign minus j indicates this is lagging behind the current by some angle. Please remember this one. So let us try to represent this one. So this can be represented in this form. The leakage flux I am representing in the external circuit in the form of an inductor. So this I am representing, let us assume the leakage reactance due to this one. So this one I am representing by X1, and the EMF induced is EL1. Let us take the core. That core is having the ideal core. That means core doesn't have any type of leakage flux. I can represent in this form. So similar is the case for the secondary. So secondary, this is my winding. So secondary side, whatever the drop is there, so that I am representing by a reactor X2, and this will be connected to load. So now again applying the second side, there will be E2 that is induced. Let us assume this is the polarity of E2. Same way, same polarity, this also will have. This will be EX2, and this will be my terminal voltage. That means the load voltage VL. Getting it? Similar is the coming for the first case. This is V1. This will be plus minus. Similarly here, the back EMF that is induced or the self-induced EMF will be E1. So we can write the equations for the same. So this I can represent by V1 is equal to minus E1 minus EL1. You agree with me? Because that minus sign is indicating that to compensate for this or representing, they are 180 degrees opposite to each other. So this will become minus E1. So minus of minus will become plus j times of I1 into X1. This is the value of E1. Similarly, in the secondary side, I can write my value of the voltage V2. V2 will be equal to E2 plus EL2. That will be equal to this value. So this I can write as E2 minus j times of I2 into X2. Agree with me? EL2 is minus j times of I2 into X2. So from this I can write my value of E2 is equal to V2 plus j times of I2 X2. V2 plus J times of I2X2, or simply this I can write as V2 minus EL2. V2 minus EL2, this will be equal to E2. Getting it? Because EL2 I am referring from this side to second side. V2 minus EL2, so overall thing that will become equal to minus sign will be there. Getting it? Minus is there, plus is there. It is V2 minus EL2, this will be plus only, right? So now let us draw the equivalent circuit by considering the iron loss component as well as the magnetizing component of the current. So this can be represented like this. The transformer equivalent, there is a current I1 is passing, there is a reactance, leakage reactance, then followed by the magnetizing component, so that I can represent like this. So this is representing the iron loss component, that is IW, this is representing the magnetizing component and X0, and the no load current I0 is passing through this, and here there is a winding, and there is a winding. You can see here I have not drawn the parallel lines because the core I have already represented in the outside. This is my voltage V1. So now coming to the secondary side. So secondary side there will be reactance X2. Remember here I have not considering the winding resistance here. I am just assuming winding resistance is equal to 0. In the next class we will discuss about the winding resistance. So this will be my value equal to V2, and there is a load impedance. This is called as the equivalent circuit with the leakage reactance and no load branch elements. Getting it? So now the phasor diagram if you want to draw under loading conditions. So that phasor diagram I can draw like this. There is a flux phi. So because of this the EMF is induced E2. Okay, let us assume some voltage V2. So some V2 I am representing here, V2 is there. Let us assume some current is passing through this, some current I2. Let us assume the load is a lagging power factor load. The current is lagging behind the voltage by some angle phi 2. So because of this current, so now some leakage flux will be produced because of the current, because leakage flux depends on the load current, how much current is passing through the winding. So this will be in phase with the current, because always the flux produced will be in phase with the current. We have seen in the last to last class, I have discussed those things. So phi L2. So because of this phi L2, the EMF is induced. That EMF will lag behind this flux by 90 degrees. Everyone agree with me? So this EMF I can represent here. It is lagging behind this flux by the angle. So this I am representing as EL2. This I am representing by EL2. So now V2 minus EL2 will be E2. So EL2 is coming as upwards. So minus EL2 will be represented like this. So this will be equal to minus EL2, which is equal to J times of I2X2. Getting it? How the E2 is obtained is clear to you. Now in order to compensate for the secondary current I2, the primary will draw the current which is called as I1 dash. Let us assume the no load current I am representing by I0. So the sum of I0 plus I1 dash will give my primary current that is drawn from the supply. So now due to this primary current or the current passing through the primary winding, there is a leakage flux, so that I can represent as phi L1 will be in phase with I1. So now the EMF induced in this will be lagging behind by 90 degrees. So let me represent with some different one. So it is lagging by 90 degrees from this. Let us assume as EL1. Getting it? So now in order to calculate the value of the primary voltage, because EMF induced in the primary, so that I can represent as minus E1, because actually it will be in phase with E2. I am taking to the primary side or to the second quadrant. So I am taking minus E1. So for this minus E1, I have to add minus EL1. That is what the equation I have written, or this is nothing but J times of I1 into X1. So when you add J times of I1 into X1, this gives my value of the primary voltage V1. So now the angle between this V1 and I1, this is called as the primary power factor angle. So in this way you have to do it. Remember here I have not considered the effect of the winding resistance. That thing we are going to discuss in the next class. So now I want to refer, let us assume the entire equivalent circuit, I want to refer to the primary side, because whenever you are calculating the numericals, because N1 is to N2 is there, I cannot apply the simple network theory application for this one, because we have to transform, because voltages and currents are different in this circuit and different in this circuit. If that can be brought to the primary side, then calculation will be easy, because voltages will be same and currents will be very easy to calculate. So in order to transfer this reactance from the secondary side to the primary side, first thing you have to remember that here the per unit reactance drop should be same whether you refer to the primary side or to the secondary side. Or what thing I have to take care, the per unit reactance drop before transfer should be equal to per unit reactance drop after transfer. So per unit reactance drop will be I1 multiplied by x1, that is the voltage drop in this reactor, divided by the voltage will be E1 I am taking as the base. So this should be same as when you refer to the primary side, because let us assume this is the primary side reactance x1, right? When you refer to the secondary side, current passing in secondary side will be I2. So let us assume this reactance when referred to the secondary side I am representing by x1 dash and the voltage in the secondary side is E2. So from this I can calculate my x1 dash, it is a reactance, primary reactance referred to the secondary side. So this I can write in the form I1 by I2 into E2 by E1 times of x1, because I1 by I2 we have already seen it is called as the transformation ratio, same thing is E2 by E1, so this becomes k square times of x1. So reactance referred from primary to secondary, I got k square times of x1. So similar is the case, I can write I2 x2 divided by E2. So when I am referring to the primary side, current will be I1 and the reactance referred to primary is x2 dash divided by E1. So this gives x2 dash is equal to x2 divided by k square. So in this form I have to refer. So you will get my doubt, why I am calculating that per unit reactance drop is same. What is the significance of this? Actually this concept is called as the per unit concept, which is generally used in power systems for calculating in electrical engineering. Let me just briefly give you the details of what does it mean. So if you want the further details, you can refer to my power system lectures, there I am going to discuss this. So let's take for example, so I am discussing the basic, then I will proceed further for remaining things that is required. Let us assume there is some voltage V1 is applied. So there is some impedance is there. So let us assume impedance is there, some current I1 is passing. Getting it? So now the current that is passing I1 will be equal to V1 divided by Z1, or simply I can tell that Z1 is equal to V1 divided by I1. V1 divided by I1. So this voltage is the base voltage and current will be the equal to base current. Getting it? So the impedance seen from your circuit or the impedance seen by the circuit will be voltage divided by the current. So if you take your transformer, the transformer there are some turns. Actually the load is connected here. Here the voltage is V2, current is passing is I2, and this is my load impedance. So what is the impedance seen from this side? Seen from your source, I want to calculate. But your source is at a difference value of the voltage. When the source is at a different value of the voltage, that impedance will not be same, because current is also different level, voltage is also different level. So in order to calculate in that case, we go for per unit values. So the per unit value will be equal to actual value divided by the base value, or this will be whatever is my actual value divided by the base value will be Z base, that will be what is the reference voltage and what is the reference value of the current. So that we have to divide by this one to calculate the per unit value. So the advantage of the per unit value will be the value will be same whether you refer to the primary side or you refer to the secondary side. That's why per unit reactance I have taken as same in this case. Getting it? So now the total reactance that is referred to the primary side I am representing by x01. This will be sum of, already the primary side one reactance is there x1, and the secondary reactance referred to the primary side will be x2 referred to the primary side, that is x2 dash will be x1 plus x2 by k square. So similar is the case, total reactance referred to the secondary side will be x1 is referred to the secondary side and x2 is already there. So this will be equal to k square times of x1 plus x2. Okay, and because of this x01, I can calculate the per unit reactance drop referred to primary will be I1 x01 divided by E1. Similarly, per unit reactance drop referred to secondary side will be x02. I have to divide with the base value. Actually, why it is coming? X02 I have to divide with the base value. Base value of the voltage is E2 and the current is I2. So that is the reason it is coming like this. It will become unitless because the units are impedance by impedance. It becomes unitless. That's why it is called as per unit value. So now let us try to prove that the per unit reactance referred to both primary and secondary will be same. So I can write as I1 x01 divided by E1. So this I can write as I1 divided by E1, and this x01 I can write as x02 divided by k square. You agree with? Because reactance referred from primary side to the secondary side, because any reactance when referred it will be divided by k square. So x02 divided by k square, the secondary reactance is referred to primary side. So this will become I1 divided by E1 into x02 divided by, that k I can write as E2 by E1, or I can represent in terms of I1 on the I1 divided by I2. So I have written both the terms. So if you simplify them, you will get as I2 x02 divided by E2. So this is nothing but per unit reactance referred to the secondary side. So we can tell in a transformer, per unit reactance referred to the primary or the secondary side will be same, and this per unit reactance is also sometimes called as percentage reactance or percentage reactance drop of the transformer. I hope that what is the effect of the magnetic leakage flux of the transformer and how to draw the equivalent circuit, and what is the effect of this leakage flux, how the net value of the voltage or what is the effect of this leakage flux is clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.